stop sharing. Now the next speaker is Professor Sai K. Vanapalli. Yes, Professor
Yeah,
Vanapalli.
I'm here.
Are you there?
Yes.
Yeah. He's there. So again, sir, I will be very brief in the introduction as far as the introduction is concerned. So I will introduce Dr. Sai Vanapalli. He is currently a professor in the Department of Civil Engineering as University of Ottawa. He completed his PhD in 1994, and his area of research is mechanics of unsaturated soils and its application in geotechnical engineering. Prior to accepting faculty position at University of Ottawa in 2003, including serving as civil engineering department chair from 2010 to 2015, he worked at various universities, including University of Saskatchewan, Royal Military College, and Lakehead University in Canada. Dr. Vanapalli has authored or co-authored more than 300 research papers and has presented 22 keynote addresses in several national and international conferences. Throughout his research career, he has received and been nominated for several awards, and most notably are the STMAC Award in 2010 and Outstanding Service Contribution to Canadian Geotechnical Society, Georges Glinksy Award of Canada, Excellence in Research in 2015 from University of Ottawa. So with this brief background, I request Professor Vanapalli to deliver his lecture on simple approaches for the design of shallow and deep foundations for unsaturated soils. So, Professor Vanapalli, again, I request you, if you are able to finish in 25 minutes, that is okay, 25 to 30 minutes.
Thank you very much, Professor Samadhya, for that introduction. Today, I'm going to present an overview of how you can design foundations, both shallow as well as deep foundations, such that we take into account of the influence of suction, or in other words, how would the design of the foundations be different from what we generally see in saturated soils. We do have a good background of saturated soils. Everyone has a very good idea of what the conventional engineering practice is, but how do we design foundations when we have to do the same in unsaturated soils? So this is how my outline would be: a brief introduction, background, and also I'll provide you theoretical studies which are consistent with saturated soil mechanics such that it would be easy to understand. Then these theoretical studies would be verified with some experimental studies and also some numerical modeling studies. Then I will provide some brief conclusions. Before I actually start, I would like to take this opportunity to actually thank the organizers. And also, before coming to Canada 31 years ago, my first conference that I attended was Vizag conference. And at that time, I have seen Professor Shashi Gulhati, and I asked him, I have an opportunity, I want to go to Canada. Is it a good idea? And he said, where are you going to? Who would be your professor? I said, Professor Fredlin. He said, okay, say hello to him. It is a good opportunity. Don't hesitate. You go to Canada, and who knows, the next time you come to Vizag, you will be doing a good presentation on your PhD research topic. His prediction has come true. I will take this opportunity to actually thank Professor Shashi Gulhati. And at that time, I did not know that he actually worked in unsaturated soils. And when I talked to my Professor Fredlin, who is my PhD supervisor, he said, Shashi Gulhati has done a wonderful work on unsaturated soils, and he would be doing the same research along similar lines. What a coincidence. What both the professors have said appear to have come true. Anyway, Let us see the old map. And if you try to see this old map here, in the orange and yellow colors, you have 60% of the world population. And these are the regions where you have soils which are actually arid or semi-arid, meaning that there is going to be more evaporation than infiltration. Therefore, the soil is going to be in a state of unsaturated condition. But we conventionally use saturated soil mechanics because that is the mechanics that we all understand. That was originally developed by our pioneers, Terzaghi, Skempton, Peck, etc. And irrespective of the region, what we try to do is we try to use the same traditional approaches, but that may not be actually valid in all scenarios. If you try to see in the world of soil mechanics, you can see that below groundwater table, soil is in a state of saturated condition. But most of the infrastructure that we actually construct is actually in unsaturated soils, whether it is foundations, retaining walls, roadways, pipelines, etc. There are many things, including the slopes. A rational approach would be to take into account of the influence of both unsaturated conditions as well as saturated conditions, such that you have a rigorous approach. I'm not going to discuss of all the things, but I would like to provide a background of how shallow foundations and pile foundations can be designed in unsaturated soils, and I will try to compare with saturated soil mechanics. I would be going a little fast because I have to cover a lot of ground, but I'll try my best to still provide all the details, but most of the information is in the papers that are already in the proceedings. We all know below groundwater tables, the pore water pressure increases in a hydrostatic condition, but above groundwater table, we know the soil is in a state of unsaturated condition, which we call as Vader zone. And here there can be either hydrostatic increase in the pore water pressure. Sometimes if there is more evaporation, there will be more suction. And when there is infiltration, soil can actually saturate gradually. So therefore, you can see above groundwater table, you have to actually use unsaturated soil mechanics where most of the soils, most of the infrastructure is in this region we actually have. But when you are saying the soil is saturated, it is a two-phase material. When soil is completely dry, again, it is two-phase material. But in unsaturated condition, you have to take into account the influence of all three phases, which is solids, which is liquid, as well as water, or soil, water, and air. So here we know in saturated soil mechanics, we use shear strength and we use modulus of elasticity as tool in the design of foundations. And now in this presentation, I would like to show how these two properties, shear strength as well as modulus of elasticity, can be used in the design of unsaturated soils, foundations in unsaturated soils. As I said, there will be a brief theoretical background, then we will verify the theoretical background with experimental studies, both in lab as well as field, and then we will have numerical modeling studies, how it can be conducted. So background, I don't have to explain this, everybody knows. For effective stress analysis, Terzaghi has given the equation, sigma prime is equal to sigma minus UW. We use this thing to determine the shear strength parameters, C prime and phi prime. As we already talked, we know the soil below the groundwater table is saturated and above you have unsaturated, so you have to take into influence of the negative pore water pressure. This negative pore water pressure with respect to atmospheric pressure is what we call a suction, and you can see there are different phases and the colors clearly demonstrate that you have all three phases. Most of us, we know, or at least it has been briefly introduced, the specific equation, which have actually extended seeing the success for saturated soils, the equation that has been by Terzaghi, which is widely used, he tried to use in the same form an equation in terms of net normal stress, which is sigma n minus UA and UA minus UW, and you have one parameter called chi, and the chi is a function of degree of saturation. So when degree of saturation is equal to 0, soil is dry, this gets vanished because chi would be equal to 0. When soil is saturated, then chi would be equal to 1. Then you would be having an equation which would be easily be able to move into saturated zone. But a more rigorous approach was actually provided by Fredlin as a part of his PhD, working under the supervision of Morgenstern. So you can see this is the sigma n minus UA and UA minus UW are the true stress rate variable. They are independent stress rate variable. So therefore, the friction that is generated due to the influence of net normal stress is not the same as matrix suction. So you cannot combine exactly into one particular equation as you see here. Therefore, a more rigorous approach would be to take into account as an independent state variable, and tan phi b is another angle of internal friction, which is a function of matrix suction. Yes, there are experimental procedures that are available, but trying to determine the shear strength from experimental procedure is very time consuming and needs a lot of equipment. So as a part of my PhD program, I have developed two approaches. If you try to see, the first part in blue is referring to the saturated soil mechanics equations, which is similar to what we already know, but in the red is the shear strength contribution that is arising due to suction. And here you have S degree of saturation to a fitting parameter called kappa. It is a function of plasticity index, and this kappa value would be equal to 1 for sandy type of soils, but it changes for fine-grained soils. There are empirical equations that we have developed. A more simplified approach would be to use this without having a fitting parameter. You can take S minus SR by 1 minus SR, where SR is said to be the residual degree of saturation. We will see what it is. And if you try to see here, all we need is angle of internal friction phi prime and C prime, which is the effective shear strength parameters, and then we can use soil water characteristic. What is a soil water characteristic? When a soil is initially in a state of saturated condition, when you are subjecting it to suction, what happens is there will be a desaturation. At one particular value, what happens is when the suction is increased, water starts escaping and air starts entering, and therefore the degree of saturation actually starts decreasing. So therefore you can see, you can do a little construction method, and you can try to see using tangents. You can find what is the point approximately where the air enters and what is the point at which it would be very difficult to actually remove air by desaturation because there will be adsorbed water, etc. So therefore, there are three zones that you can classify, you can have in terms to explain how the soil water surface actually changes. Boundary effect zone where the soil is saturated, and in the transition zone, air enters and there will be a steep rate of desaturation, and by the time you are coming to here, the desaturation becomes very, very slow. So we have developed a technique of using, I have already shown, approach 1, approach 2, and you can use soil water characteristic curve as a tool for predicting the shear strength. And in a similar way, we can also use soil water characteristic curve for predicting the modulus of elasticity. In the same fashion, soil water characteristic curve can be used for predicting the bearing capacity. Bearing capacity both under drained condition as well as undrained condition. So therefore, if you try to see here, based on what I have said before, here is a completely saturated condition, and you can see the degree when the degree of saturation is close to 1, the angle of internal friction phi prime is equal to phi p. And once the air starts entering, the rate at which the shear strength starts increasing starts to decrease, and therefore there is an increase, but not as much as you see in the saturated zone. But when you're in the residual zone, if it is a sandy type of soil, you can see the strength starts decreasing, but in types of clays, it will be still increasing. But in some other type of clays, like silts, you will be seeing there will be a nominal change. So the same approach that we have used here, as I said already, can be used for even predicting the modulus of elasticity. I'm not going to go into all the details to save some time. So here are some experimental results with which we have predicted using both the equations. There is a good comparison. If you try to see here, the symbols represent experimental results and the continuous lines are the predicted envelopes. And if you are cross-plotting, what happens is the slope of shear strength versus net normal stress would be equal to, the slope would be phi prime. In other words, phi prime can be treated as a constant value. That means we have a very simple equation for predicting the shear strength. One part would be the same as saturated soil, and for the other, you need soil water characteristic. So therefore, now we have seen there is a parallel between the shear strength of saturated soils and shear strength of unsaturated soils. Let us try to see the Skempton's approach. Skempton has taught us what total stress analysis is. Here, phi u is equal to 0. And you can see we can do an unconsolidated undrained test or an unconfined compression test to actually get this information. So again, based on experimental studies and trying to take, and we have taken some information and we developed an equation of Cu unsat, which would be equal to Cu sat, that is unconfined compression stress, plus taking the influence of metric suction, and you have two parameters, nu and mu. So there are empirical equations that can help us to find what these values are, and then we will be having a good comparison. All we need is unconfined compression test value, metric suction, and soil water characteristic curve. You can see soil water characteristic curve can be used as a very good tool. So now, Terzaghi and Skempton have given us the bearing capacity equations in undergraduate classes. Everybody is introduced with these topics. So therefore, I wanted to see how we can use this approach. It should be a simple approach, but still that can be extended for unsaturated soils. That is the key objective of this particular presentation, which is the work of several PhD students, but I have combined all these pieces of works from these students to provide theoretical background, some experimental background, and also numerical studies. The numerical studies is more recent work that has been undertaken by the two students who are co-authors, who are Mengshi Tan and Cindy Shinting Chen. I'll show their pictures. Now, what are the theoretical studies? Now, let us see how you can modify effective stress approach that you have seen for saturated soils to unsaturated soils. This is the equation that we already know, Terzaghi's equation, C dash NC plus gamma df NF, gamma df NQ plus 0.5 gamma B and gamma. This is everybody knows these things. This is for a strip footing. And now these are the bearing capacity factors. And now one of my students, Fatih Muhammad, has developed a technique. And if you try to see here, the stress ball that is going to develop is typically below a certain depth. In this particular case, it is 1.5 to 2B. All you have to do is find the centroid. So this is the unsaturated zone. Try to find what is the centroid and then take the average suction value and use that average suction value and put it to the equation. I'm not going into all these equations. All the information that you need is soil water characteristic curve and angle of internal friction. So all the other parameters would be the same. Similar to shear strength, we have a kappa. Now for fitting the bearing capacity, we have another parameter, psi. So now we have seen 3 sands have a value of 1, and for other soils, the value actually changes. You can use that and then compare the bearing capacity. There is a good comparison. We will see the experimental results in a little while. Okay, now the same approach can also be extended for total stress analysis for undrained loading conditions using Skempton's approach. So here, undrained shear strength, we already have seen an equation, and there is a relationship that we can actually develop. So now this is the equation that you already know for saturated soils, but for unsaturated soils, there will be a little modification, and again, the terminology would be exactly the same. So, as I said, I'm not going to get into the details of elastic modulus. Similar approach can actually be done. You can see an equation similar to the shear strength, similar to the undrained shear strength. You can have an expression that would be developed, and here you need 2 constants, alpha, beta, and these values are fitting parameters. You can get, I have already shown this value, depending upon your plasticity index, you can get your mu and mu. And for modulus of elasticity, for alpha, beta values also, you have relationships. These are the theoretical studies. That is about the shallow foundations. Let us have a look at pile foundation. I'm seeing it now. This is an end-bearing pile, or in general expression, ultimate load carrying capacity is shaft friction plus point end resistance. So what we have done is we have developed an equation similar to the shear strength and similar to the modulus of elasticity. So you can have an expression that can be developed. I'm not going to all this equation. Please have a look into the paper which provides all the details. Now that is for effective stress analysis, but for total stress analysis, we know that there is alpha method, beta method, and lambda method. We have modified alpha method, beta method, and lambda method. We know that there is going to be skin friction that would be developed all along the length when it is fine-grained soils. So it is going to be typically undrained load conditions. We also have to know what is the immediate load carrying capacity. So therefore, we adopt alpha method, which has been modified. I'm not going to all these equations, but we already know that unit skin resistance would be a function of undrained cohesion, effective stress, and wall angle friction. So this is the equation that we already know. Now what we have done is this is a function of Cu. Previously in saturated soils, it is Cu. So in unsaturated soils, it will be Cu unsat. And we already have Cu unsat equation that we have developed. So therefore, we can incorporate into this equation, and that would be useful for finding out what is the carrying capacity for fine-grained soils. There is beta method, which is given by Berlin and Chandler. So again, I'm not going into greater detail about all this equation, but this is well known in the literature. All the undergraduate students are also introduced to this thing. So now what we are trying to do is we are trying to add the contribution that is going to arise from the matrix section, and that would be again a function of relationship based on soil water characteristic curve. You can use that as a tool, and then you develop an expression something like this. You also have lambda method, which is a combination of both alpha method as well as beta method, because there is not going to be a true effective stress analysis or a true total stress analysis. There are scenarios which are somewhere in between. So in those cases, you can use modified lambda method. So experimental studies, we have seen the theoretical background, which is consistent with saturated soils. So Some laboratory tests have been conducted, and also some field tests have been conducted for shallow foundation. The same way for deep foundations, I will show some laboratory tests and also some comparisons from other studies. Now, this is the University of Ottawa bearing capacity equipment. Those of you who have read the autobiography of Terzaghi. Terzaghi has used a wooden tank to develop the equation of bearing capacity of saturated soils. Q ultimate is equal to C dash NC plus gamma DNQ plus 0.5 gamma B N gamma. I told my student Fatima Muhammad, you see, Terzaghi had a wooden tank, and that too, it was having some leakage problem. That's why he has focused on sands. Now you have a steel tank, and then try to now develop an equations along similar lines what Terzaghi has developed. So therefore, this student, Fatima Muhammad, has developed equation, and I have already shown some theoretical background about this thing. What is the average section value from the centroid? What is the average section that you can actually measure? And that would be, you can calculate and then use it into the equation, theoretical equation that we have developed. And if you try to see here in this case, he has done the test, both the surface loading as well as penetrate. Also, the foundation is placed at a certain depth, footing is placed at a certain depth, and you can see that the bearing capacity increases rapidly. Even a few kPa of suction can increase the bearing capacity by lots. So therefore, we can understand that the suction is actually bringing the particles into a closer state of contact, and therefore there's an additional friction that is developed, and that is going to contribute to extra shear strength or extra bearing capacity. In the same tank, again, the student has used some cone penetration test. So we have tensometers to measure the suction. We have a tank water supply, which actually can saturate the specimen, the tank, and also by bringing down the water, you can actually increase the suction. So therefore, cone penetration test has been done, and then we have developed equations for saturated sand as well as unsaturated sand. We also have taken some.
Yes, we have 5 minutes.
Okay.
You can take 7 to 8 minutes.
Okay, thank you very much. Please give me a couple of extra minutes. Okay, so you can see there's a good comparisons. Now we have the same way we did experimental results. You can see how it has been conducted in the paper. But what you can see here is you can see that the estimated bearing capacity and measured bearing capacity there is a very good comparison. Okay, we also have done the field test near an airport, very sandy type of soils at a low water table and a close to saturated conditions. Plate load tests have also been conducted. Standard penetration tests have been conducted, and we have developed equations, and you can see, and also we have compared with some of the data that is published in the literature. You can see again that these equations are working well. So there is a good comparison between measured and estimated values. In the same way, we have done tests for the plate load test. This is a recent, pile load test, the recent test, and we can see that we changed the groundwater table and we have developed the equation. The theoretical background has already been provided, and you can see already available equations which have been modified, and you can see there is a good comparison with plus or minus 20%. So we did again alpha method, beta method, and lambda method, and the laboratory we have done the test, and you can see that there are good comparisons between the measured and estimated values. We also have done pile groups. I'm not going into all the details, but you can see that we also have developed an approach of how you can calculate the ultimate bearing capacity, and those are in those papers. So I'm not going to discuss a lot about the pile groups because I have focused the theoretical studies mainly with the single piles and mainly the shallow foundation. I will very quickly move through numerical modeling. You see, even though we have some theoretical studies, etc., it is very important for us to actually understand how you can actually model using the software that is available, such that you can take into account different scenarios. You can actually do certain kind of sensitivity analysis to understand. So we actually recently we have been using Abacus. Abacus facilitates to take into account the nonlinear behavior of unsaturated soil. That means the nonlinear behavior of the shear strength as well as modulus of elasticity can be incorporated into it. So all we need is saturated shear strength parameters, saturated modulus of elasticity, and the soil water characteristic curve. Again, I'm not going to go into all the details, but if you try to see here, where the suction variation is more, we can have more closer mesh. Afterwards, you can have a rougher mesh. And Abacus is a good one where you can write your own subroutines and take into account nonlinear behavior of unsaturated soils. You need soil water characteristic curve. That information is directly included into Abacus software, and using the theoretical background into the subroutine, and you can see, you can compare. We have compared with Abacus, which provides a better relationship with the actual experimental program compared to MESA, and I'm showing you some comparisons again using Abacus and the measured bearing capacity in MESA, and you can see again the results are good. So in the same way, we did some modeling studies for fine-grained soil, shallow foundations. Again, there is a good comparisons, bearing capacity and matrix suction. In other words, what I'm trying to impress is, if you have simple tools, saturated shear strength parameters and soil water characteristic curve, even for field studies, you can actually, you can take into account the conditions that are available in the field and model. You can also do parametric analysis where the groundwater table has been changed, and then you can see the sensitivity analysis, how the bearing capacity increases, how the load settlement behavior actually changes, because we also need the information of the settlement behavior. So therefore, load versus deflection behavior is also important.
Excuse me, Professor.
Yes, I'll wrap it up. 1 minute. Okay.
Conclude in 5 minutes, please.
Excuse me, how many minutes?
5 minutes.
Okay.
Okay, let us say 5 to 10 minutes.
5. Okay.
Please.
I would have appreciated to know this a little bit earlier. Okay, file foundations. Also, you can model these things. Now, if you try to see here, the modeling has done. On one side, you can see the bearing capacity, pile bearing capacity in coarse-grained soils. Here, pile bearing capacity in fine-grained soils. You can see that you can incorporate the information of the shear strength parameters plus the soil water characteristic curve, and you can try to see the comparisons. So we have actually changed the groundwater table to get the information using the theoretical analysis. And also, if you do the modeling, you can see for one diameter pile that we have taken here, you can see there is a good comparison. So what we have done here, if you try to see, is we are comparing theoretical studies with experimental studies with modeling studies, and modeling studies with, again, theoretical studies. In all these things, there is a good comparison. Again, here, sensitivity analysis or parametric study can be taken with groundwater table. And what you can see is, in the groundwater table, when it is 0, which is a saturated soil mechanics theory, you would be having a very low capacity, but you can see as the groundwater table is at a greater depth, the carrying capacity actually increases. So therefore, with ground improvement techniques, etc., if you're able to control the groundwater table, you can try to take into account of the influence of suction and try to see that you can take advantage of the suction and then see that your load carrying capacity is much higher. Here, we are trying to compare the calculated shaft bearing capacity of a fine grained soil, and we are predicting this with the finite element technique. So again, we used abacus. In the abacus, we can have subroutines. In that subroutine, the information of the theory that we have developed can be put into that. And then if you can model, if you try to see here, alpha method, beta method, and lambda method with different colors here, you can see that there is a good comparison, which is plus or minus 20%, which is good. So therefore, you can see there is a consistency between the experimental methods, within the theoretical methods, within the modeling methods, that gives confidence for the practicing engineers. And the theoretical framework that is developed is consistent with the saturated soil mechanics, and it is very easy to understand. So now I'm coming to conclusions. So therefore, you can see that we have NumPros. When we want to see that unsaturated soil mechanics has to be taken into practice, it should be simple. It should be easy to understand. In the last 20 years, I had been working with my students to see that a framework that is consistent with saturated soil mechanics. Only then the practicing engineer can understand. And in all these cases, as you have seen, first we take the saturated shear strength or saturated modulus of elasticity, and you combine the additional component that you are going to get from suction. And then we have shown that from experimental studies, theoretical studies, and numerical modeling studies, there is a good comparison. So these are simple modifications for interpreting the saturated soils such that you can get the unsaturated soil behavior. So such theory or such modeling or such methods would be definitely be encouraging for the practicing engineers. So I would like to thank the NSERC, which is a main funding agency, and also University of Ottawa for providing me with the funding and facilities. As I have shown you many pictures of who have done this work, it is just a hard work of many PhD students. For example, what I have shown here is a work that has been summarized over the past 20 years. More than half a dozen PhD students have worked, and these two students have helped me, Mengshi Tan and Shinti Sheng. I would like to thank for their contributions in summarizing this presentation and the paper. And I thank Indian Geotechnical Conference, Vizag chapter, Indian Geotechnical Society, and also Indian Geotechnical Journal, encouraging to see that our work is promoted. Thank you very much.
Okay, I think this question is to Professor Vanapalli because it is 12:57, so it must be, it's not written. So have you done any practical study of very high loads to provide any value engineering?
A good question. We are working along those lines. The work is under progress. So therefore, at this time, we, as I've shown you, I have used some of the information that is already available from the literature, which has been done by professors like Brio, who was the past president of the International Society of Soil Mechanics and Foundation Engineering. I have provided some comparisons. And also we have done for the pile foundations in expansive clays. So this is the information that is already published in the literature, but we have checked with our methods. And this is the paper, the pile foundation paper has been published in Soils and Foundation Japanese Journal that can be seen. But if you try to see this paper that we have presented to this conference, the references are there. And also if you closely see, some of the comparisons are there with field studies, which are large scale studies.
Okay, there is one question from Swati. Thanks for the wonderful presentation to Professor Vanapalli. Practically, the worst design criteria is assuming soil as saturated soil. How do we arrive saturated shear parameters from UU test done on unsaturated soil? Can we use your formulas to reverse calculate the saturated parameters? Something like back analysis?
Yes, you can also do that back analysis because we have developed the equations in such a way. What you can actually try to do is you can take a specimen, do the unconfined compression test, use the coefficients of mu and nu, and then once you provide a comparison with the saturated thing, you can, if you have the information of soil water characteristic curve, you can go backwards. So it is called a 1-point method. Once you have 1-point method and the soil water characteristic curve, you can do that. You can do that. You can actually see how your unconfined compression test value can change from saturated condition to unsaturated condition. You can do that.
Okay, there is another question from Dr. Raghuveer Rao. Thanks for interesting presentation, Professor Sai. How far or how close we are to introduce unsaturated concepts into codes of practice?
Very good question. So with Canadian Foundation Engineering Manual, I am one of the persons I'm working with some things related to expansive soils. If you see South Africa code, South Africa has actually introduced this shear strength equation into literature. It is evolving. China is actually trying to also work in this particular direction. Yes, it is still not, this is still considered as an emerging area. We are making some progress, but there are some countries which I have already said to you, South